semester for no reason.
Yeah.
Okay, folks, if we can get started. So I have a couple of logistical things to go over before we get into the content. Pickles is in my office today, so this is just me keeping an eye on her. So the first logistical thing I wanted to mention is I've been getting quite a number of emails from folks asking for enrollment codes for 4920, the technical writing course that will be offered next semester, which is awesome. I need to get all those enrollment codes from the department folks, which I expect that I'll have either by the end of the day today or by tomorrow. But there is no enrollment cap for that class, so just I'll send you the code when I get it, but don't worry necessarily that you're not going to get into the class if you don't have it. There's enough space for everybody there. I've been getting a few emails as well about advanced microcontrollers, ECE 5760, which is the other course I'll offer next semester. The enrollment cap for that class right now is at 40 people, and the reason for that cap is the amount of hardware that we actually have to work with. So it's a pretty fixed cap. If you are not currently enrolled in that class and you would like to be enrolled in that class, just keep an eye out in the first week or 2 weeks of the semester. For that class in particular, there seems to be a lot of flux in the first week or so. And oftentimes that's because it's worth knowing, incidentally, if you're signing up for this class, that the hardware that we use for that class is not a microcontroller. It's a system on a chip. So it's an FPGA and a ARM processor. It's one of these DE1 SoCs. So it's a Cyclone 5 FPGA, which communicates to an ARM processor on which we actually boot Linux. And the two communicate with one another over shared memory. So the format of that, or the structure of that class, is identical to this class in that we have 3 guided laboratory assignments followed by a final project. Each of those laboratory assignments, unlike this class, where we're just writing C code for the microcontroller, each of those laboratory assignments will involve writing C for the ARM side, a bunch of Verilog for the FPGA, and then getting the two to talk through this proprietary bus system that we'll talk about. So every lab involves C, involves Verilog, and involves this memory mapping. It's a lot of Verilog, right? So if you're interested, if you like Verilog, you're going to like that class. If you're not so keen about Verilog, think about it maybe. And if you are enrolled in that class, I would recommend that you start reading for it like now. There's a lot of reading for this class, particularly for the first lab. So you might consider going to the course website for 5760, which if you just Google ECE 5760, this is what the website for that class looks like at the moment. You might consider going through and starting to do the reading for Lab 1, for instance. Lab 1, we're going to build a differential equation integrator for the Lorenz system in particular, which is pretty fun. Lab 2, we're going to simulate the 2D wave equation on the surface of a drum and then generate drum sounds. So it's real physical. Remember how I talked about there are a few methods for generating musical instrument sounds, one being spectral matching, another one being FM synthesis, a third one being physical simulation. In Lab 2, we deploy that third option, physical simulation, on a drum. So we're actually simulating the 2D wave equation at audio rate, and the challenge of that lab is how big of a drum can you generate and still meet your audio timing deadlines. And then the third lab is calculation and rendering of the Mandelbrot set, which we've talked about in this class. This is a speed challenge. So we calculate and render this set as fast as you can just using the ARM, and then you accelerate that to the greatest extent that you possibly can using the FPGA. And that's I'm going on a little bit of a tangent, but that's the general flavor of this whole class. What the class really focuses on is hardware acceleration. So in each of the labs, we'll take some algorithm and baseline it on the ARM, and then we'll see how much we can speed up the calculation of that algorithm using the FPGA. In Lab 2, the calculation that we happen to be accelerating is the 2D wave equation. In Lab 3, it happens to be the Mandelbrot set. And then in your final project, you'll be asked to come up with some project application that involves some ARM stuff and some FPGA stuff. Bruce?
I think for Lab 2, the one group managed to get a 170-way parallel solver, right? So 170 independent CPUs running.
Yeah, it is wild. So if you're interested in FPGAs, you might be interested in this class. I just like to tell people about that because the name of the class, Advanced Microcontrollers, people sometimes think that it's more microcontrollers, and it's a little bit different than that. So just so that you're aware. Okay, any questions from anyone? Yeah.
It says the prerequisite recommended to be designed using embedded operating system. Do we suggest us to take that class before we do this?
So yeah, the question was that the recommended one of the recommended prerequisites for Advanced Microcontroller is embedded, and that's because we boot Linux on the ARM side of this system on a chip, so we'll be interacting with it via the Linux command line interface. Some familiarity with that is really helpful. So if you've taken Professor Scavira's class, for instance, where you've gotten a bunch of experience with Linux stuff, then it's helpful in this class.
It's not like you'd have to be familiar with the OS, not like just the command line stuff.
Right, yeah. If, depending where you are sort of in your academic career here and how much time you have left, the trajectory that people often find most, what's the word? The sequence of classes for which you're sort of picking up the most relevant knowledge as you go for the next class is usually this class, followed by, I would say, 5725, which is Professor Scavira's class. So in this class, we're doing bare metal programming of microcontrollers. Bare metal meaning there's no operating system here, right? We're just writing C code, and the only code that lives on this microcontroller is the stuff we put there. In Professor Scavira's class, ECE 25, you're working with Raspberry Pis, not the RP2040, but the actual Raspberry Pis on which you put Linux. So now you have an operating system on there as well, and you gain experience with Linux command line stuff. And then in advanced microcontrollers, ECE 5760, what we then do is take a Linux environment, kind of similar to the one that you would have been exposed to in 5725, and tack on an FPGA and get the two to talk to one another. So that's a sequence that you might consider if you have the time remaining here to do so, is 4760, 5725, 5760. I generally advise against taking more than one of those at once. People do it all the time, and you're adults, you can do whatever you want. Taking more than one project class at a time makes the end of the semester just not so fun. Makes it a little bit hard to learn because time gets pretty crunched. People do it every year, and oftentimes at the end of that year, they'll come up and say, you were right.
It is not sane to take 3 design courses.
Any other questions? Do you have a question? Oh, she can't hear. I wonder why. Okay, thanks for letting me know. Let me just take a moment here. It appears as if the audio is working. Okay, sounds good. Anyway, I hope it's recording okay. Any other questions from anyone? Yeah.
So I want to take advanced micro without taking embedded, but I've worked with Linux before and I understand Linux. Will that be okay?
That would be okay.
Okay.
That would be okay. Yeah. If anyone is in the situation where you don't have all the prerequisites and you're wondering whether or not you'd be okay, just please come talk to me about it. Sometimes the answer is yes, sometimes the answer is maybe not. But if you don't have all the prerequisites for a class, definitely talk to me about it and we'll figure out your particular circumstance. Yeah.
Is taking 5725 as a co-rec to advanced microcontrollers a bad idea, like you said, or is that even possible?
So in terms of prerequisite content, it works okay. In terms of your sanity and how much time you have to be a human being, I advise against it.
It's okay because I'm on the wait list.
Okay.
That's a sanity wait list.
Look at the wait list to see if I get to commit my complicated system.
Any other questions? We do have lab this week, and we're starting on final projects this week. So I'm going to ask each week that you all submit a progress report for your final project. And I believe that the content that I expect in each of those reports is outlined, I believe, on the webpage, but I'll double check that. But it's not much. All that I'm essentially asking for is, here's a bulleted list of the stuff that we accomplished this week. Here's a bulleted list of the stuff that we plan to accomplish in the coming week. And here's how many hours we spent working on this project this week. That's what I'm looking for. And that will start, I'll ask for the first of those progress reports before your assigned lab section next week. So we have this full week to start on the first week of your final projects. And as I mentioned before, starting next week, so starting on Monday, we will have more lab time instead of lecture time. We're about at the point in the semester where I feel like that's the way that I can be most helpful to all of you, is just to spend more time in lab. The Monday lecture times, the lab is actually occupied. So what I'm going to do is go through and look at the lab reservation timesheet, and I'm going to put together a calendar of when the lab will be open every week. And I'll indicate on that calendar when I will be in the lab, and I'll post that on Canvas so that you know all of the opportunities that you have to come work in the lab. You are expected to continue to attend your assigned lab section. That's sort of where we do our weekly, it's not incredibly formal, but our more formal sort of weekly tag up of how things are doing. But then beyond that, you are welcome to come into the lab whenever works for your schedule. Why did we lose that? Hold on a second. Let me see if I can bring this back. Okay. All right, anything else from folks? It's Pickles. She's okay. All right, so then in that case, I want to talk today. I sort of just briefly introduced one of the final peripherals that I want to talk about, which is the Watchdog timer last week. Last lecture, I sort of introduced it conceptually, and I want to talk about it in more detail this semester. This lecture is going to be a little bit different as well because I've been trying to get one feature of the Watchdog timer to work for a demo this week, and I haven't gotten it debugged yet, but I want to show you where I am in this debugging process because at this point in the semester, you all know a lot about this system, so it might be the case that you go, hey, like here's the issue. So we'll see. And also, if I put this online, maybe some kind internet person will have something to say about it. So I want to talk about the Watchdog timer. Let me remind you conceptually what this thing is for. So let me pull up the data sheet. The notion of the Watchdog is that, where is it? The Watchdog timer provides a mechanism by which the microcontroller can reset itself. It can do a software reset of itself. Why might that be useful? The notion is that if you have one of these things deployed in some location where it's difficult to go access to reset the system if it needs resetting, or alternatively, if you have it deployed in some sort of a situation where it's hard for me to come up with a concrete example of this, but perhaps you're having the microcontroller interact with some system or some external thing which makes it susceptible to getting in a hung state. And we could talk about sort of what that might mean specifically, a specific example. But suppose you have the microcontroller talking to something and it's supposed to go through some process, but you have this concern that given the nature of what it's doing, it might end up in a state where the software hangs. What the Watchdog allows for you to do is notice that your software has hung, and if you don't reset this particular peripheral, people call this petting the Watchdog, incidentally. If you don't go in and pet the Watchdog, then the Watchdog will do a software reset of the system to put it back into a known initial configuration. So conceptually, it's very, very similar to, remember way back to when we talked about the timer peripheral. I talked about these alarm registers associated with the timer peripheral. We would put a 32-bit value in those alarm registers, and when there was a match between the value in that alarm register and the lower 32 bits of that 32-bit incrementing timer, then an event would occur. In particular, an interrupt would get thrown. We would maybe enter an interrupt service routine or something. This is very similar, where just like that alarm register, we're specifying a certain amount of time into the future. And this peripheral is paying attention to what it's actually doing is counting some number of clock ticks. So we're specifying a number of ticks to count. It's noticing the number of ticks that it receives from the clock that drives it, which is driven from the, it's derived from the reference clock. But it's counting clock ticks. And if it counts a specified number of ticks without you having gone in and resetting it, which is to say, reset that number of ticks again, so you zero the number of ticks so it starts counting up again. If it counts the number of ticks that you specified, it executes a software reset. And there's some interesting bells and whistles associated with this peripheral in particular that we can talk about. Okay, but fundamentally, that's all that it's doing. The other, so there aren't many registers associated with this. They're all actually listed here. There is a control register, which allows you to configure and control this thing. We can take a look at that if you all would want to. There's a load register. This is the register where we specify the number of ticks that the watchdog should count before the software reset occurs. And if we were to go into the C SDK and look at the SDK function that we call to pet the watchdog to reset it, what that's actually doing is going in and resetting the value of that load register. The other kind of interesting thing that this will do, oh, I'm sorry, it's not going in and resetting load per se. It's going in and zeroing the number of ticks that have been counted so that we start counting up again towards load. The other sort of interesting thing that this will do is it will log the reason that the last reset occurred. So suppose that the system rebooted because you unplugged power and then plugged power back in. The system will know, by checking this reason register, you can determine whether the most previous reset was because of a software reset caused by the watchdog timer or because of some sort of power on reset or a brownout reset. It knows the difference so that you can take perhaps a different course of action if you know that the watchdog reset your software as opposed to some sort of power on reset or something like that. And then there's a series of scratch registers, and the data that's contained within these scratch registers is retained between software resets. So you can put information in these that will be there when the system comes back alive after a software reset. And these are used in sneaky ways. These can be used in sneaky ways to actually modify the boot sequence of the RP2040. So we'll talk through the boot sequence at a high level here in a moment, but there's a series of events that the microcontroller goes through when it boots up. One of the first things that happens is the ring oscillator turns on. That ring oscillator is then used on to turn on a bunch of other peripherals. At a certain point, the processors get turned on and they go through their own sequence of events. One of the steps in that process, in that boot sequence process, is to check the value of one of these scratch registers. We'll double check here in a moment, but I believe it's actually scratch 4. And if you put a number in there that the data sheet calls the magic number, what that affects the boot sequence in such a way that instead of going through the rest of the process as usual and booting from the external flash memory, what it will then do instead is look in a couple of these other scratch registers for a program counter, a place in SRAM to jump to, and it will look for a stack pointer. We'll store those two pieces of information in others of these registers. So in the event that it finds the magic number, then instead of booting from external flash, it will instead go to the place in SRAM specified by another one of these scratch registers and execute whatever it finds there using the stack pointer that you've also specified. So when we were brainstorming final project ideas, one of the hallucinations that we had was, wouldn't it be kind of interesting to write some sort of custom bootloader for this thing, where maybe you could add new code to it via some mechanism that isn't dragging and dropping the UF2 file over. Maybe this is a handle that you can grab to start to work on something like that. Maybe. I've been playing with this. That whole thing that I just described, incidentally, that's what I was trying to get a demo of today, and I don't have it quite working yet, but I'll show you where I am in the debugging process. The amount of explanation for that, there's not a ton of documentation, honestly, for this particular feature of the Watchdog timer. The extent of the documentation is here on the scratch register section, where it tells us that the 8 32-bit scratch registers can be used to store information between soft resets, blah, blah, blah. The boot ROM checks the Watchdog scratch registers for a magic number on boot. This can be used to soft reset the chip into some user-specified code. And then it points us to this other section of the datasheet, which contains a little bit more documentation. And what this section of the datasheet tells us is that the magic number is that hex B007C0D3. Okay, so we put that magic number in Scratch 4, and then we XOR our desired SRAM entry point with that magic number and put that in Scratch 5. We put our stack pointer in Scratch 6 and our entry point in Scratch 7. And in principle, this then modifies the boot sequence to direct the system over to that particular point in SRAM for execution. Kind of interesting. Kind of interesting that we can do this. Let me just show you the boot sequence here quickly. They have kind of a nice graphic of it. So let's go look at the boot sequence. Make this a little bigger. So here's what I'm talking about. This is what they call the, there's a sequence of events that they call the hardware-controlled boot sequence that happens before this. This is things like turning on the ring oscillator, stuff like that. And then we enter what they're calling the processor-controlled boot sequence, which is what this graphic is showing us here. And what happens? Well, the following order of events occur when the system boots up. Both cores enter the boot ROM. Each core looks up which core it is. Remember that in the SIO, the single cycle IO block to which both processors communicate, that's the block that contains all the peripherals to which each of the processors requires low latency access. There's a register in there called CPU ID. And if core 0 reads the value of that register, it gets a 0. If core 1 reads the value of that register, it gets a 1. So it's a mechanism by which each core can figure out which core it is. So each core does that. It asks, which core am I? If the answer is you're core number 1, then it just goes to sleep. Core 1 goes to sleep in the boot process until we wake it back up with one of those multi-core launch core 1 commands that we used in labs 1 and 2, right? When we were launching code onto core 1, we did that ourselves. If it's core 0, then it checks the value of some flag. The next thing that it does is it checks that scratch register associated with the Watchdog peripheral. And in particular, it's looking at scratch register 4 for that magic number. In the event that it finds the magic number there in that scratch register, it does not go through the whole rest of this boot sequence. What it does instead is set the stack pointer and jump to the specified entry point and start executing code from that particular entry point. Which, by the way, as I read this data sheet, that entry point has to be in SRAM. Incidentally, I'm the most common use for this Watchdog timer is not to do this crazy stuff. The most common use for it is just to, in the event that your software hangs, it does a normal software reboot, right? And there's an SDK function set up to do that. I'm just talking about this particular feature of it because it's kind of unique and interesting, I think. Questions about this? Yeah.
So if you do this trick, then Flash is not enabled to store programs at all.
Not as far as I understand. Yeah. but I'm still experimenting with this. I mean, I'm sort of explaining it to the extent that I presently understand it, which is, I have some more understanding here to do. But like I said, you guys can help me with this now. So that's why I want to present this kind of stuff that I'm still working on. Okay, so let me just show you some example code here. I want to look at the Pico examples repository. In particular, in the Watchdog directory, there's a hello Watchdog example, which shows a very basic use of this thing. So we're including a few libraries, including the hardware interface library to the Watchdog peripheral. We initialize standard I/O. We then enter these conditionals where we're calling a function called Watchdog caused reboot. This is accessing that register that I mentioned previously that's keeping track of, was the previous reboot because of a Watchdog caused software reset, or was it because someone unplugged and replugged power or something like that, right? So it is figuring out whether or not it was the Watchdog timer that caused the most recent reboot. In the event that it was a Watchdog timer, then it prints that message, I was rebooted by the Watchdog, and it returns 0, which means that this whole thing stopped, it exits, right? Otherwise, it'll tell you this was a clean boot, which is to say that it was booted up just by turning on power or something like that. It wasn't a software reset. It then calls an SDK function, Watchdog enable, the first argument to which is the amount of time that you would like for the Watchdog to count before it will reset the system. So you have to go in your code and reset the Watchdog at time intervals that are less than this. The units of this, incidentally, are milliseconds. This is 100 milliseconds. The SDK then converts this to clock ticks under the hood. We're specifying it in milliseconds. We enable it here, so it starts ticking. What this particular example then does is go through a for loop and prints a little message that's updating the Watchdog, and then it calls Watchdog update, which goes in and resets that tick counter, right? So it starts counting up again. When we enter this, we stop updating the Watchdog, so we allow for that tick counter to count all the way up to 100 milliseconds. A Watchdog reboot will occur. When it reboots, we'll come back. We'll notice that it was the Watchdog that caused that most recent reboot. It'll print this message and then it exits. Right? So this is a simple example that's meant to demonstrate how you might implement something like this in your own application code. That makes sense? And let's see here. So if we take a look at, this is a slightly modified version of that, but let's just take a look at, for instance, that Watchdog update function. What's it actually doing? It is going in and resetting that load value register in. It's the load register in the that we just looked at in the data sheet, right? Which is actually the first thing I said. I said that it was going in and resetting the load value. Then I corrected myself to say, no, it's zeroing the ticks. Actually, I was right the first time. It's going in and resetting that load value. Okay. There is another SDK function. This is the one that I've been experimenting with, and I'm still trying to get it to work, called Watchdog reboot. And if we look at the CSDK guide, let's see, RP2040 CSDK. Let's look at the CSDK guide, and in particular, let's take a look at the Watchdog section. And there's a function here called Watchdog reboot. And what we see is this function allows for us to define actions to perform at a Watchdog timeout. It takes 3 arguments, all of which are unsigned ints. The first argument is the program counter. This is where we want to jump in SRAM on reset, as far as I understand. The second argument is the stack pointer. This is the stack pointer that we'll use when we boot back up to this particular location in SRAM. and delay milliseconds, just like the function that we just looked at. What this is doing is putting a certain amount of ticks into that load register so that we count up as high as we want to until this actually takes place. And then in principle, what should happen is, if we have initialized the Watchdog timer using this particular CSTK function, which is going in and under the hood, what this is actually doing is modifying those scratch registers associated with the Watchdog peripheral. So it's going in and putting that magic number in scratch for the program counter and the stack pointer at the appropriate scratch registers, so that the next time this system would boot up after a software reset, in that boot sequence, because we've called this function, that boot sequence would notice that magic number in scratch 4, and then go to the program counter and start executing whatever it finds there. Principle, that's what it does. The arguments, incidentally, you may have noticed in the data sheet for the multi-core section, there's a CSTK function called something like multi-core launch core 1 with stack or something like that. And in that, you can specify a non-default stack pointer for that core 1 should use. And the argument there is a pointer. It's pointing to a location in memory. The argument here is an int, which, as I interpret this, is sort of, you are taking a memory address, casting it to an int, and using that as the argument to this function, is how I'm interpreting what I find here and what I'm finding in the implementation of this in code. That said, it may be the case that my interpretation is wrong and I need to figure it out, because I haven't gotten it to work yet. so I don't really know. But I'm doing something wrong, and I need to figure out what precisely it is. So the demo that I am trying to get to run, is I have some function up here, which I'm using that prefix that we talked about briefly in a previous lecture to store that function in Flash, right? And all that function is doing is turning on the LED. And what I'm trying to get to happen is I'm just doing a slight modification of the standard Watchdog demonstration, where instead of calling Watchdog enable to turn on the peripheral and specify a timeout, what I'm doing instead is calling a Watchdog reboot, where I'm specifying the program counter, the place in memory to which I would like to jump on reset. And I'm specifying that as the address of that function, where that function lives in SRAM. And then I need to specify a stack pointer. So I've tried a few methods for doing this, but my most recent attempt, what I did was declare a big old int array, and I pointed to the top of that array for my stack pointer. It turns out that the stack actually counts down, right? So I pointed to the top of that array, and then I specified, I don't know, 200 milliseconds for the timeout, and it will go through and it will indicate that it has been rebooted by the Watchdog, but I haven't yet gotten it to go into that function. Not exactly sure why yet. Hopefully in another day or two, I'll be able to figure out what exactly is going on here. I haven't gotten that figured out just yet. So how am I going to go about debugging this? I think my next, I want to find mechanisms for adding information here, right? Like that's, you don't know what else to do when you're debugging. Just start to try to add information in whatever way that you can. And so I think what I'm going to do next, how's Pickles? He's okay. I think what I'm going to do next is go in and throughout this process, check the values of some of those registers and see what actual values those registers are assuming in this process, to see if I am actually configuring the registers in the way that I think I am. I may not be. Maybe that's the error. In any case, that's what I'm sort of trying to figure out. Any questions? Yeah.
Why did you decide like the 50,000?
Somewhat arbitrarily. I just wanted a big int array. Yeah.
The type of the input of the function you wrote for Watchdog reboot.
The type of the input for what?
Watchdog reboot, unsigned long. Oh, so it's unsigned in 32.
It takes a bunch of unsigned ints as the input, not pointers, but unsigned ints. So if we go look at the implementation of this, let's see here. Yeah, I mean, it's doing about what we would expect for it to do based on our reading of the data sheet, which is it's going in, it's calling a hardware clear bits to the control register of the Watchdog peripheral to turn it off, pause it for a second while we're doing our configuration. Then it's going in, it's checking if there's a non-zero value for the program counter argument to this function. In the event that it's a 0 value, then it goes through a normal boot sequence. But it sees if we've specified some non-zero value for that program counter. In the event that we have, it goes in and it puts that magic number in Scratch 4. It XORs that magic number with our program counter and puts it in Scratch 5, puts our stack pointer in Scratch 6, and puts the program counter in Scratch 7. And then it calls a Watchdog enable, which is well, it's up here. Well, no, it's right there, actually. So what that one's doing is yeah, it's making sure that the peripheral is paused, going in and doing some configuration, setting the load value. Incidentally, I said that under the hood it was converting this to ticks. Here's where that's happening. It's taking our delay in milliseconds, multiplying it by 1,000, and then multiplying that again by 2. Why is it doing that? If you go read the errata for the RP2040, there was actually a small error where this decrements by 2 instead of 1 accidentally every cycle, so we have to double that. That's why that's there. So I'm not sure yet, but I'm enjoying poking around trying to figure this out. Soon enough, I think. Yeah.
So if it doesn't go into the function, does it just hang, or does it boot normally, or what?
It appears to just hang. Yeah.
How do you know that you're not getting to the test function?
So I know that I'm not getting to the test function, or I suspect that I'm not getting to the test function because all the test function does is turn on the LED, and I'm not seeing the LED turn on. And I've unit tested that function just by calling it in main, and you know the function's okay. It just turns on the LED. It does what it's supposed to do. But after a software reset, I'm not seeing this function get called and executed. Yeah.
In the block diagram, it said that the crystal oscillator and all of the clocks get turned on way after it would break off and run that code. Does the GPIO need those clocks running to do that kind of stuff?
That's a good question. In this diagram here?
Yeah, because none of the clocks would be on when you jump to the entry point. So your code might be running, but then like never, the peripherals aren't enabled.
That's an interesting thought. Yeah. I'll investigate that. Yeah, Bruce?
ROS gets started in the block, doesn't it?
Yeah, the ring oscillator gets started before any of this. I think there's a diagram up here. So yeah, I mean, this is describing briefly what's happening before that diagram, which is we apply power to the chip. The run pin is high. This is you can reset the chip by attaching a button to run, right? So it's checking whether run is high when we power on the chip. We wait for the voltage out of the voltage regulator to stabilize. The ring oscillator starts. That provides a clock source to the clock generators. The reset controller, execute in place, memories, bus fabric, and processor are all taken out of reset. And then we start doing this, is the sequence. So I'm going to keep poking at it. I'll let you know what I figure out. Anything else about this? There was just one more document that I wanted to point folks to because I thought it might be relevant for some of you for final projects. So the other thing I wanted to point you to is down here on the course web page in the links section under Raspberry Pi technical documentation. there's a document here called Hardware Design with RP 2040. What this describes is, suppose that instead of using the Raspberry Pi Pico as your development board for the RP 2040 chip here, suppose you wanted to design your own PCB that featured an RP 2040 on it. Right, so maybe for some reason you wanted a different form factor, you wanted to include some peripherals on this circuit board along with the processor. What this document describes is what's all the external stuff that you need to make sure is on the circuit board in order for this to actually work. So it walks you through a few different design examples. It starts with what they call the minimal design example, which is to say the minimum amount of stuff that you need just to get this thing running like a Pico. And then it walks through some other stuff, like suppose you wanted to add VGA on here, or suppose you wanted to put an SD card on with this thing. How might you integrate that into a circuit board? So I just wanted to briefly point out some of the things that you would include. One of the things that they recommend is there are two different voltage supplies that are required to run this thing. One at 3.3 volts. And another one at 1.1 volts. But what they're specifying is that there's actually an internal voltage regulator that will generate that 1.1 volt supply from the 3.3 volt supply. So all that you actually have to do is provide a 3.3 volt supply. There are a few mechanisms by which you can do that. On the Pico itself, when you plug it in via the USB connection, one of the pins in that USB connector has 5 volts on it. And there's a regulator on board that's regulating that down to 3.3 volts to actually run the RP 2040 that's on the Pico. But this is suggesting how you might build that onto your own board as well, a system like that. Some other stuff that they recommend that you include on your own custom RP 2040 board include a collection of these decoupling capacitors. I imagine that this is a familiar concept to most folks, but the notion of these decoupling capacitors is that they are filtering out any supply noise. So if your power supply is a bit noisy, these capacitors are smoothing out the power supply. And the other thing that they're doing is, suppose that you're drawing a lot of power rather quickly, they do provide some amount of energy storage. Right, so that if you try to draw a whole bunch of current quickly, you can get some excess power from these decoupling capacitors. Right, so they have on here recommended values for those decoupling capacitors and a recommended placement for them. It matters where you place things like these on a PCB.
They provide like an example of schematic for like the minimal design.
I believe they do. Yeah. Some discussion here of the internal voltage regulator, in particular because they specify that you should have a capacitor nearby the pin associated with this internal voltage regulator. There's some guidance here about how to connect the external flash storage on which your program code lives to the RP 2040. Recommendations in terms of what are your options for external flash devices? What features does an external flash device need to have in order to be compatible with the RP 2040? It talks through that, and here too, it gives some recommendation in terms of layout and things like trace length, right? This is a rather high-speed connection, so they're making simple recommendations like you want to make sure that these traces are relatively short. So you want for this to be in close proximity to the RP 2040. They make recommendations with regard to the external crystal oscillator. The one that's on the Pico that we're using is at 12 megahertz. It can accommodate some other frequencies. I'll remind you from our discussion about the clocks on the RP 2040, this external crystal oscillator is an example of one of the clock sources. So remember that there are a handful of clock sources on the RP 2040, one being the crystal oscillator, the other being the ring oscillator. Remember that the ring oscillator is fully internal, which is kind of nice, but you can't guarantee the frequency that it's ticking at, which is kind of not nice in some applications. And then this crystal oscillator will feed a few phase lock loops to increase the clock rate to a few peripherals. What this too, it makes some recommendations about where you would place this crystal oscillator and about what the acceptable frequencies are for this external crystal oscillator. And then finally, it makes some recommendations with regard to hooking up a USB connection to the RP2040, how you might do that, and I/O headers and such. So here's a overall recommended schematic for a minimum design, and a list of some of the external flash chips that would be compatible with the RP2040. And yeah, nothing much more to say about that. If you keep scrolling down in this document, it describes some, more advanced PCB design recommendations for accommodating things like SD card, audio stuff, VGA, all that kind of stuff. So, again, depending on what you're doing for your final project, you might find this useful. Designing a custom PCB for your final project for this class is not without precedent. Folks have done this. If you want to do this for your final project, you just need to budget it in to that project in terms of both money and time, right? So you need to accommodate for the amount of time that it will expect for you to actually procure one of these PCBs from some sort of fabrication house. Or if you're a Maker Club member, you could try using that PCB mill in there if you wanted to. Yeah.
Can that do traces small enough for the RP2040?
I don't know the answer to that. I don't know.
Maybe.
Any other thoughts?
How would you flash a code if you use your own flash memories? Do you have to configure anything about QSPI to that?
You don't have to do any of that sort of configuration. The chip will ship with the code, the ROM boot code in place, so that if you set up the flash memory connection correctly, and if that flash memory is compatible with the RP2040 as described in this document and the data sheet, it'll boot.
Okay.
You'll be able to program it. Anyone thinking about doing this? Maybe? Yeah, it's one of those things that depending what you're doing, maybe it's useful. If you're so inclined, it's also just an interesting exercise, but a little ambitious, maybe. Okay.
Do we own the right to resell the custom board we built?
You have the right to resell your custom board. Boy, I'm going to withhold an answer for that because I need to look that up. Okay, so what that means, we're about out of time for today, so let me just wrap up. We have one more lecture to go then, and then we're going to transition to labs. In the next lecture, what I plan to do is, last semester, how to phrase this? So you guys are all like seniors, master students, and I've had conversations with a few of you about, after we graduate here, do I want to go to grad school? Do I want to go to industry? Trying to figure that kind of stuff out. And last semester I did an experiment that turned out to be kind of helpful to some folks, which was, I'm just going to start giving the PhD dissertation that I gave so that you can get a sense of what a PhD in this kind of stuff looks like. And I won't get the whole way through it, right? But if I would have really appreciated seeing something like that when I was at your position in my own academic career, right? Because I didn't really know what graduate school in this kind of stuff really meant. So that's my plan for next time, is basically I'm just going to start doing a PhD dissertation, and we'll see how far we get, and folks can interrupt me and ask questions as much as you want. But hopefully maybe that can help if you're trying to make these sorts of decisions, maybe that's helpful in informing that decision. So that's my plan. Okay.